So today we'll study interval scheduling problem, and for this also we'll design a very simple greedy algorithm, and we have studied some greedy algorithms before. First was for fractional knapsack problem, second for Huffman encoding, and this is the third. And in each case our observation is that the algorithms are very simple and their time complexity is also very low. So for both fractional knapsack, Huffman encoding, and this problem also, time complexity will be only n log n. And so greedy algorithm, they have three characteristics. The first is we incrementally build the solution. Second is the greedy choice property, means local optimal implies global optimal. So at each step we make our choice using local information, and the result is we get globally optimal solution. And third is we have a single sub problem. So here also same thing we'll observe, and we'll prove its optimality again using induction. So for this we'll follow the reference book Kleinberg and Tardos Algorithm Design. It is an excellent book for learning how to design algorithms. So first it is shown that there may be several heuristics for greedy algorithm. We'll analyze one by one each and taking short examples and show that they will not work. Then finally our final heuristic will work for the small examples. Then later we'll proceed for proving its optimality using induction. So first we define what is interval scheduling problem. So this is a very simple problem. Suppose we have a classroom and there are requests for lecture, and the requests are in the form of duration, start time and end time. So for a single day there are several such requests, and our objective is to schedule as many lectures as possible in the single classroom. So this problem is called interval scheduling problem. So we take very simple example and start with some possible heuristics that we can have. So first we take a simple example. We make a timeline and set of heuristics. So suppose for example we make a timeline like this. So first we make a timeline 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and so on. So there are intervals, several intervals. These are requests. So for example, first interval we can have from starting from 1 up to 10. This is first interval request. Start time is 1, finish time is 10, and several possibilities, several other requests. For example, we can take like this: first request, second, third and fourth. Start and finish time, this is 2 and 3, 4 and 5, 6 and 7, 8 and 9. So this is one instance of interval scheduling problem. We are given 5 intervals. First is the longest interval from 1 to 10, 4 short intervals, 2 to 3, 4 to 5, 6 to 7, 8 to 9. Now the problem is select the intervals. So intervals, they should be non-overlapping. This is the requirement. Select non-overlapping intervals such that the number of selected intervals is as large as possible. So in this case, you can easily see that optimal solution is choose the 4 short intervals, 2 to 3, 4 to 5, 6 to 7 and 8 to 9. This is the optimal solution. Now we can have some heuristics. So we'll test some heuristics for designing greedy algorithm. So we use this notation of start and finish time. So the problem we define as we are given a set of requests, number them 1 to n, 1 to up to n, set of requests with start time and finish time. So ith request, for ith request, start time we denote by si and finish time by fi. So this notation we use. So first heuristic what we can evaluate is based on starting time. So we call this heuristic earliest start time first. So first heuristic we evaluate heuristic 1, earliest start time first. Earliest start time first means what we do is first choose the interval with the lowest possible start time. Select the interval and remove all other intervals which overlap with it, and again repeat the same process once again. So we evaluate this heuristic on this our first example. So according to this heuristics, earliest start time is for the interval from 1 to 10. So we choose this according to our algorithm. Once we choose 1 to 10 interval, we have to remove all these 4 small intervals, 2 to 3, 4 to 5, 6 to 7 and 8 to 9, because they overlap. So this heuristic we get only a single interval. So this may not be it does not satisfy greedy choice property. It is not giving optimal solution. So this heuristic fails. Earliest start time first. This is our first heuristic, and this is not, greedy choice property is not satisfied for this. So next we test some other heuristic. So here we can observe why our heuristic fails, because we have ignored small intervals. So we may think that if we choose small intervals first, then we can get better solution. So next heuristic we apply is smallest interval size first. Next heuristic we try smallest interval size first. So earliest start time first, it was based on sorting this sorted order of SI. So sorted order of SI means once we choose a particular interval, we have to remove all other intervals which overlap. So here it is also very similar. Here we see sorted order of Fi minus Si. Consider sorted order of not Si, Fi. Finish time minus start time. So again here also, once we choose the interval, we have to remove all other overlapping intervals. So now we test this heuristic, and this works for this example. So first example, just sort by size of the interval. So we get these 4 small intervals. So first we choose this. So we have to remove all other intervals which overlap, and there is only one other which overlaps. So this largest interval we remove this. Next again we repeat the same process. Now we have three other smaller intervals. Again we choose the next one. So the only overlapping interval, it is already removed. So we consider next, we take this, next we take this similarly, and finally we take this. So we are getting optimal solution. So for this instance, algorithm is giving optimal solution. But we should check for other possibilities also, and we'll observe that this is also not the optimal. It does not satisfy greedy choice property because of the second example. So second example we take. Now second example we consider, in which second heuristic will fail. So once again we make the timeline. We make the timeline and see a simple example. Starting with 0, can make 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So here we have 3 intervals. First we can make like this, from 1 to can make 4, 1 to 4, then we can make from 5 to 8, 5 to 8, and one more from 3 to 6. We can make this larger like this, make this from 0 to 4, second one from 5 to 10, and this from like this 3 to 6. So this is counter example for second heuristic. So here we can see we have 3 requests, 3 intervals. First, shortest interval size is from 3 to 6 of size 3. Next we have 0 to 4 of size 4, and 5 to 10 of size 5. So according to this our algorithm, we have to choose this shortest one. So once we choose this, we have to remove the other 2 intervals. So we are getting only a single interval. So you can easily see that optimal solution is 2 intervals. Choose these 0 to 4 and 5 to 10. So second heuristic also, it does not satisfy the greedy choice property. Now next we test our third heuristic. So third heuristic is so in third heuristic what we do is we count the number of other requests that are not compatible, means we have a conflict, and take the request that has fewest number of non-compatible requests. So select the interval with fewest conflicts. Now I will explain this idea. So here you can see for first interval how many conflicts are there. For the interval from 3 to 6, it has 2 conflicts. First the interval 0 to 4 and second is the interval 5 to 10. For 0 to 4, compute the number of conflicts, means number of overlapping intervals. It is only 1, 3 to 6. For this also 5 to 10 also, it is single interval which is overlapping is 3 to 6. So our next heuristic is smallest number of conflicts first, we can call it. Third heuristic we write smallest number of conflicts first, this heuristic. So this works for this example. So if we apply this heuristic to this example, so first we choose this 0 to 4 interval we can choose, and we can remove this because we have a conflict. Then we can choose this, so we are getting optimal solution. But again, this is also not optimal. Greedy choice property is not satisfied, and we can see with a very simple example, another counter example for this. Smallest number of conflict. Here conflict means number of overlapping intervals. We call it conflict. So yes, select the one with the smallest number of conflict. Here conflict means smallest number of overlapping intervals. So why we are selecting 0 to 4 interval? Conflict means number of overlapping intervals is only 1. Here also number of overlapping interval is only 1. But for this it is 2. It is overlapping with this and also this. So we do not choose this. We choose either this or this. We can choose both. This is the algorithm. So counter example we take for this, several short intervals. Again we make a timeline like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here we have several short intervals. We can take of length 2 each. First we have we can take from 1 to 3 intervals like this: 1, 2 and 3 like this. Another from 0 to 2 we can take, 0 to 2 like this. We can make this larger, 3, just make it of length 3. So we have 0 to 2, 0 to 2, then we have from 1 to 4, 1 to 4 each, 1 to 4. Then one overlapping interval we can make from this 3 up to 6 we can make, 3 to 6, then one from 5 to plus 3, 8, 5 to 8 we can make, 5 to 8, then we can make from 7 to 10. 7 to 10 we can make 7 to 10, and then from 9 to 12 we can make 9 to 10, 9 to 12, 3, 9 to 12, 1, 2 and 3, each from 9 to 12, 9 to 12, and finally one more from 11 to plus 3 is 14, make this 14. So this is the counter example. Here we have several short intervals with different levels of overlapping. So we apply our algorithm, shortest conflict first. So we can calculate the number of conflicts for each so you can compute, for example, this. If we take this 0 to 2 interval, so I will write the number of conflicts using a circle. So how many intervals are overlapping? 3, 1, 2, 3. So right here 3. Similarly compute for each. For this number of conflicts 1, 2, 3, 4. Similarly for each, 4 each, 4, 4, 4. Then for 3 to 6 interval, it is 1, 2, 3, 4. Here also it is 4. 5 to 8 interval, only 2. Then 7 to 10 interval. 7 to 10 interval, it is 1, 2, 3, 4. Right, 4. Then we have this 9 to 12 intervals. So number of conflicts is 1, 2, 3, 4. 4 each. 4, 4, 4. Then 11 to 14. Number of conflicts is 3. So shortest number of conflicts first. So we choose this 5 to 8 interval. It has number of conflicts 2. Remove all which are in conflict. So we have to remove this. This is removed. This is also removed. Now again we apply the same process. Next smallest number is 3. So we choose this and remove all these. All these are removed. And finally we choose this. All these are removed. So we have selected 3 intervals. These are 0 to 2, 5 to 8 and 11 to 14. So here also you can easily see this is suboptimal. The optimal will be simply choose these 0 to 2, 3 to 6, 7 to 10, 11 to 14. 4 intervals we can satisfy. So this is also, it also does not satisfy the greedy choice property. Now our final heuristic that will satisfy the greedy choice property is shortest finish time first. Fourth heuristic we see shortest the request I for which correct, shortest finish time first. Finish time first. So here we sort by fi values and choose the fi with the smallest value. Remove all intervals which are overlapping and again repeat the same process again. So we'll show that this satisfies the greedy choice property. So before that we'll test our this heuristic on the 3 given examples and see that it is giving the optimal solution. So first we apply to our third example. So just sort them using smallest finish time first. So smallest finish time is 2. We choose this interval we choose, and remove all conflicts. So these are the conflicts we remove. Next we get is this. We choose this, again remove all conflicts, this conflict is removed. Next shortest finish time is this. With 10, take this, remove all conflicts. Finally we take this. So we are getting optimal solution. For our third example, similarly for first and second also we can see. For the second example, shortest finish time is 4. We choose this and remove the overlapping interval. Next we take this. Again we are getting optimal solution. And our first example, here also we can see shortest finish time, we choose 2 to 3, remove this conflict. Next we take this and this. So 3 examples we are observing that smallest finish time first algorithm is giving optimal result. So now we'll prove this formally using induction. So this is our algorithm, and what approach we take for proving this. So greedy choice property, yes, choosing smallest finish time first and removing overlapping intervals gives globally optimal solution. So this will prove, and the proof strategy we make use is so we compare our algorithm with the optimal solution. So the strategy that we use is call our A. So we start with let A be the set of intervals output by our algorithm. So we compare our set A with optimal set. We compare A with O, where O is optimal solution. Now our objective is to prove that they have same size. To prove that number of elements in A is same as number of elements in O. This is our objective. So first thing we observe that A is a compatible set of requests, and this is very easy to observe. A is a compatible means no conflicts. Set of intervals, and this is very easy to observe because we are choosing an interval with smallest finish time and then removing all other intervals which are in conflict. So at the end the set we get is it does not have any conflicts. So this is our first observation. Now how to proceed with the proof. So greedy algorithm stays ahead. We use this strategy that greedy algorithm stays ahead of optimal. Stays ahead means in a way either it is having the same quality as optimal or better quality. So this will prove, because we are building our solution incrementally, so we compare our incremental solutions. So this strategy we use, and we use induction in this proof. So some notation we will use in this proof. So let I1 up to ik, I1 up to ik be the set of requests set of requests in A in the order of addition to A. So I1 up to ik, these are the set of requests in A in the same order, means with the smallest finish time first order. We use this notation, and similarly for O also. For O we use similar notation. Addition means in the set you are adding. Similarly for O also. So for O let the order be in which they are added J1 up to Jm. J1 up to Jm. Now our objective is to prove that M is equal to K. To prove M is equal to K, so that our solution is optimal. And here also our assumption is that they are sorted in the sorted order, left to right order of intervals, left to right ordering. Left to right ordering means J1 starts first, finishes first, then starts J2, finishes second, and so on. So left to right ordering, both our set O as well as set A. So it will simplify our proof. So this is our notation we follow. So now we make one observation that we have this finish time of I1. First I1 is finish time of J1. So this is our observation. Why? Because our algorithm follows smallest finish time first. So we are taking interval I1. It has the smallest finish time. So finish time of I1 is smallest among all finish times. In particular, this Fji. So this is our first observation, that finish time I1 interval finishes first before J1 finishes. So here, so in this way we can show that this is the idea that greedy stays ahead. Greedy stays ahead of opt. So first task of our algorithm finishes first before any other solution. So this we will prove in general. So this is the idea behind greedy stays ahead. So we have to prove this. So this is already proved for first interval. It is obvious because of the greedy algorithm. Now we'll prove this in general. So we'll prove that for all, we'll generalize this by induction. R less than or equal to k, we have finish time of IR is at most finish time of JR. So this is the idea behind greedy stays ahead. Means our algorithm, its rth interval finishes before rth interval of any other solution. This is the idea behind greedy stays ahead, and basis case is already proved because of design of our greedy algorithm. Now we'll prove this by induction. So basis is already proved. How to prove this by induction? So proof is by induction. Proof by induction. Basis is already proved. Basis is this. This is the basis. It is already proved. Now we assume that let r greater than 1. Basis very simple. What is the design of our greedy algorithm? Choose this interval with smallest finish time. So this is the idea. Fi1 is the smallest possible among all other values, in particular Fj1. Very simple idea. So this is for first interval. Now same thing we want to prove for any general. Fir is at most Fjr. So here we are applying induction. So basis is already proved. So we assume that we have assume it for I r minus 1 index, assume. So our assumption is f of I r minus 1 is at most f of j r minus 1. This is our assumption, and we have to prove that Fir is at most Fjr. So we make a diagram of this condition, induction condition, on the timeline. So here we have a timeline, and we can make something like this, like this. This is I r minus 1, and this is j r minus 1. So here you can observe that finish time of IR minus 1 is less than finish time of JR minus 1. This is our induction hypothesis. Now we have to prove the same for rth interval. So just see the case when this is it possible that it is not true? So I will make the diagram with the opposite, means which is not true, and get a contradiction. So the contradiction case will be something like this. I will make the diagram like this. This is our IR, and we can make JR. This is our JR. So if our induction hypothesis is not true, then it should be this case. So finish time of here IR is greater than finish time of JR. So here can you observe any contradiction? Very easily you can observe. Is there a contradiction here in our algorithm? Yes, correct. So here you can easily observe our algorithm follows smallest finish time first. So it should have selected this JR, not IR. So this is not possible. Not possible means the only possibility remains is our induction hypothesis. Fir minus 1 is at most f of JR, no, IR JR. So we have proved that greedy algorithm stays ahead. So now what it means? It means that finally what we get is, so just applying this for kth symbol, kth interval. So we get this Fik, finish time of Ik is at most Fjk. Now we observe this. So now we ask the question, can we have more elements in our set? And again we get some contradiction. So we have this, and m is greater than k. So suppose that we have m greater than k. So this implies there is a request gk, there exists jk plus 1 in O. So here our objective is to prove that m is equal to k. This is our objective. So if m is not equal to k, so k is the last element of our last interval of our algorithm A. So the only possibility is that when m is not equal to k is that m is greater than k. We will show that this is also not possible. So if m is greater than k, then what will happen? We have interval jk plus 1 in O, and it starts after jk. So it is something like this. Here we have jk, and after that we have jk plus 1. So it means our algorithm A has not finished yet. It has to choose this also. But our assumption is that our algorithm ends at A. So again this is not possible. So we have proved that m is equal to k. So this proves the optimality. Next we compute the running time. So running time is very easy to find. So what we have to do is sort. First we have to do is sorting. Time complexity of shortest finish time first. First algorithm. So first thing we notice, we have to perform sorting. Sort using fi. Sort using fi values. So this step takes big O of n log n. So we sort and choose the interval with smallest finish time. After doing this, we have to remove all overlaps. So here we have to maintain a data structure for efficiently doing this. So we construct an array. Construct for efficient implementation an array of s 1 to n, storing si values, si equal to small si. So we create an array of n elements which stores the si values. So we choose the smallest interval, and using this array we scan the array from left to right and remove all conflicts. So choose i's in increasing order of fi values. So once we choose, then simply scan the si array and remove all conflicts. So once we select the first interval, then scan such that scan it until this sj is greater than f1. So once we take the first interval, simply scan the array until we get Sj value at least F1, so that all conflicts are removed. Again, we repeat the same process again and again. So we have to scan entire array only once. So total time complexity is. Hmm? No. J is the first interval which is not in conflict with the first. Not in conflict means it is not overlapping. Hmm.
First interval in the array that we have created.
What?
First interval in the array that we have created for storing the set of optimal choices of intervals which are not overlapping. What exactly is this?
Okay, so I will explain this. So here we have done sorting. Construct an array. So we have sorted based on these Fi values. So once sorted, you can assume that the elements are numbered 1 to n in sorted value of this Fi value. Simply choose the corresponding, store the corresponding Si values in the data structure I. Then once first element we choose, first element means first element with the smallest Fi value. Once it is chosen, simply scan the array from left to right order until Sj value becomes at least F1 and continue like this. So you have to scan the array only once. This is efficient data structure. Takes only linear time. So net complexity you can easily observe is big O of n log n. So here also we can observe three properties of our greedy algorithm. I think same examples we can take. Take this example. So the three characteristics of the greedy algorithm are. So first is incrementally building the solution. How we are incrementally building the solution. So take for example this. First we take this as interval. So this is our partial solution. Next we add this, then this, then this. So we are incrementally building the solution. This is first property. Second is the greedy choice property. Here greedy choice property we use is choose the element with smallest finish time first. Then remove all conflicts and repeat the same process. So local optimal is implying global optimality. This is greedy choice property. Third is single subproblem. So single subproblem, once we choose this, remove the conflict, we get a smaller subproblem, a single subproblem. So all three properties are satisfied. Any questions? Okay, thank you.
Like every time we make the greedy choice, we have to scan S and remove the element.
Yes. Once you select an interval, you have to remove all conflicts, all overlapping intervals. So this is the reason we make an efficient data structure S.
But then in the worst case, like if we have to take all the n intervals, then we have to scan S n times.
Not n times. It is in sorted order of finish times.
Okay.
Sorted order of finish time. So only once you have to scan.
Okay. Immediately we
Only scan until F1. So once you choose 1, scan until Si becomes at least F1.
okay.
So scan it once. Now we'll see a sample run of the shortest finish time first algorithm. We will take the same example as given in the book by Kleinberg and Tardos. the algorithm design book. So here we have a set of intervals given. There are in total 9 intervals on the timeline. Now step 1 of the shortest finish time first. Algorithm. So step 1 is we have to sort in increasing order of the finish time. So we sort and number them from 1 to 9. So in this sorting I will write them as 1 is the smallest finish time. After that we have 3, so we label them as 1 and 2. After that we have 5, so write it as 3. Then next we have is 6, write it as 4. Then we have 9, write it as 5. After 9 we have 10, write it as 6. After 10 we have 11, write it as 7. After 11 we have 14, we write it as 8. And finally we have 15, write it as 9. So we have sorted the intervals based on the finish time. Now for in this the same sorted order, we write the start time of each interval. So from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We have only 9, so just only up to 9 is required. So just write the finish time and start time for each. So for 1, start time is 0. 2, start time is 0. 3, start time is 2. 4, start time is 4. Then we have 5, start time is 7. 6, start time is 0. 7, for 7 start time is 8. 8, start time is 13. 9, for 9 start time is 12. So smallest finish time, we take this 1, take this interval. So its finish time is 1. Starting from 1, we remove all intervals having start time up to 1, less than 1. So just remove this 3. Second, third interval, it has start time of 2. So next we take this, take third interval, its finish time is 5. So next less than 5 finish time, we simply remove. Next we have 5, finish time 7, we take 5. Its finish time is 9, so remove this 6. So this 6, we observe that it overlaps with 1, 3 and 5 also. So we have not removed earlier just due to efficiency, because the later intervals, they will remove it. So later interval, in case of 5, we have 7 up to 9, finish time is 9. So we get overlap here, so okay, we can remove it afterwards also. So just remove for saving our time complexity. So we remove this, we have finish time 9, so remove 7 also. Then next we have 8, it has finish time 13. 8 has finish time 14, not 13. Start time is 13. So 7 we remove. Next we have 8, so we take this 8. 8 is taken, and its finish time is 14, so we remove this. So the number of intervals we get is 4 intervals we are getting.